All right, my friends. Happy Friday to you all. That's kind of loud, isn't it? Turn that down a bit. All right. We'll go ahead and begin. Last time we were talking about the Aldol reaction. And I gave you a problem, and this was related to looking at the product of an aldol reaction and be able to see what the starting material was. One of the ways you're going to recognize this as an aldol product is to start looking at the positions adjacent to a carbonyl. Alpha is adjacent, beta is the next one beyond that. We call this an alpha-beta unsaturated ketone. And alpha-beta unsaturated carbonyl compounds are aldol products. And in thinking backwards, sometimes it's helpful to think, okay, what was the intermediate immediately before this alpha-beta unsaturated carbonyl compound? So recall that usually, or we get these alpha-beta unsaturated carbonyl compounds from the corresponding beta-hydroxy alcohol. And the beta-hydroxy alcohol is also an aldol product. And recall that the bond we make in an aldol reaction is this one between alpha and beta carbons, where this section would have been the enolate, and this section would have been the carbonyl compound. Okay, so if we split that up there, and for this, at this point, you know, like I've told you in the past, this problem looks terrible because there's a ring in it. If you just did this, suddenly it maybe wouldn't be so bad anymore. So you have to learn to ignore what doesn't matter in order to deal with the chemistry that does. But if I separate this up into the enolate portion and then the carbonyl portion, that's what I've got, right? This is the alpha carbon, this used to be the beta carbon, here's the carbonyl carbon, and of course I would get that enolate by removing a proton from that ketone. And I can number the atoms to make sure I've got the same number of carbons in the starting material as I do in the product. Let's see, 1, 2, 3, 4, 5, 6, 7. Numbering carbons is a great thing to do when you're dealing with problems with rings, just to make sure you don't mess up. So, and if we draw that starting material, 1, 2, 3, 4, 5, 6, 7, in a slightly different way, this is what it comes from. Okay? Now, that might be troubling to you because if you zoom in on this starting material, there are multiple kinds of alpha protons. Okay, so you might have been worried. We get this product from removing this alpha proton. And when that alpha proton attacks the other carbonyl, that's 6 atoms away, you form a 6-membered ring. But you might have also been concerned about the possibility that this alpha proton would attack the carbonyl, and that would be 4 bonds away. So let's draw the product that you would get if you made an enolate out of alpha carbon, the orange alpha carbon, and had it attack the carbonyl carbon. So this will be, and you know what, I'm going to stop numbering 2 different ways because that's confusing. We'll just say that orange alpha carbon is 3, All right. And that's going to make a new carbon-carbon bond with carbon 6. The enolate here is going to attack the ketone on carbon 6. So here's carbon 6. Carbon 6 has a methyl group on it, and after it's attacked in the aldol reaction, it would have an OH group on it. And then let's see, we have between carbons 3 and 6, we have atoms 4 and 5. So here is 4, here is 5. So this would be the alternative product from attack of orange alpha, removal of orange alpha proton to get an enolate, and then that enolate would attack, right? So why do we have any reason to suspect one of these is preferred over the other? What do you think? Yeah? Okay, why? Stability, good. This is an equilibrium, so the most stable product is the observed one. Why is it more stable? Less ring strain. Yeah, right. When you can form preferentially a 6-membered ring, then that's over a 4-membered ring. The more stable ring is the major product. All right. This is an example of an intramolecular aldol reaction. When you do an intramolecular aldol reaction, you pair, you link two things that are tethered together in the same molecule. And intramolecular reactions are fast because the two reactive parts don't have to swim around very long before they find each other. They're chained together to begin with. All right? All right, questions that you want to ask about that? Yeah?
So this one, would you want to use, what was it called?
Would you want to use LDA? You could. It would be overkill, though, because equilibrating conditions are just fine. Yeah. And yeah, so you could still use hydroxide. And that may be troubling because this requires you to go through the less stable enolate, right? The less substituted enolate. But think of the energy diagram this way. You have your starting material, and it's true that you have the more stable enolate here. This would be the one where you remove a proton from the more substituted alpha carbon. But that leads to a less stable product. Right? Whereas here, if you remove the less substituted alpha proton, you do have to go through the less substituted enolate, which is less stable, which is why I've drawn it higher in energy. But that will lead to the more stable 6-membered ring product. And provided we have enough energy to go over all of these transition states and explore every minimum, we're going to get the more stable product, even though it passes through a less stable intermediate. Yeah. Yes?
So we do get a very small proportion of the 4-membered ring.
Would we get any of this? Well, that would depend on how much of it would we get. That would depend on the relative stability of these two. Organic chemists have actually measured ring strain, and they can tell you how much less stable a 4-membered ring is than a 6-membered ring. Oh, by the way, I guess for comparison's sake, we could also draw the alpha beta unsaturated version so that we're comparing apples to apples. By the way, I hate that game. Gosh. I mean, I know it was fun to begin with, but then it's just, especially when you play with young children, it gets really tedious. Anyway, organic chemists can tell you how much more stable a 6-membered ring is than a 4-membered ring. The difference in stability, I think, is in the 5 to 10 kilocalorie per mole range, and that translates into, at room temperature, multiple factors of 10, probably 1,000 to 1 in terms of product ratios. So yes, perhaps some, but not really enough to even observe. All right, other questions? Yes?
So the first step would be
That's right. First step would be to make the enolate by removing a proton, in this case the less substituted purple proton, to make the enolate. And then you'd have intramolecular attack of that enolate on the carbonyl carbon to give your tetrahedral intermediate. Okay, good. What else? Yeah?
Could you use sodium ethoxide?
Could you use sodium ethoxide here? Yeah, that would be fine. Hydroxide's cheap. So, and you do the aldol reaction in general in water, so it's convenient. But no, you could use, yeah, go ahead.
Are there cases where you would not want to use hydroxide and you only want to use sodium ethoxide?
I imagine solubility, if you were dealing with something that wasn't soluble in water, but you could get it soluble in ethanol, then ethoxide would be a good base, I guess. Okay? All right. Yeah?
Could you just explain really quick how the let's see, the dicarbonyl on the right ends up being the unsaturated?
Okay. So the first step would be to, oops, there we go. The first step would be to remove this proton with the base, right? To give your enolate. Second step is enolate attacks the carbonyl. That would give you this molecule with this oxygen negatively charged. It would get protonated. Then to get to the alkene from here is an elimination reaction wherein the base removes this proton first to give you, and I'm not going to draw that intermediate separately, to give you a negative charge here where it's stabilized by resonance. Then those electrons, negatively charged carbon, can kick down and kick off OH minus.
So the elimination, is that part of the aldol reaction?
The elimination is that part of the aldol reaction. Well, technically we're accepting both of these as aldol products. And because it really depends on relative stabilities which one you isolate. So I'm going to draw you both of them, and to get from this one to that one is the elimination step. If I am asking you for a mechanism, you will know what the starting point and what the ending point is, so that'll be unambiguous. If I ask you for products, I can accept either one of those as the answer. In a synthesis, you can use either one of those as the product of an aldol reaction depending on what you need. Yeah?
So in general, when we're doing synthesis problems, do we just always assume that there's water around the protein?
So in general, do we assume there's always water around to protonate tetrahedral intermediates? It depends. So watch the solvent and watch what your base is. If it's LDA, you're doing that in anhydrous conditions. So there's no sources of protons until the end when you do aqueous workup, when you wash the solution to neutralize everything. But no, this aldol reaction, you can do it in water, so you've got a ready source of protons. Okay, so so far we've done aldol reactions with a ketone or an aldehyde with itself, and then we've done an intramolecular aldol reaction. But a question we could ask is, what if we want the enolate to be different from the thing that gets attacked? People call this a crossed aldol reaction. And it's tricky. And in fact, you got to be careful or else it won't work. So let me give you an example of something that might be a problem. Let's suppose I want to use this aldehyde and this ketone, and I want them to react together. And my desired product, let's say my desired product is the one where the ketone acts as nucleophile and the aldehyde acts as an electrophile. I'm going to abbreviate the benzene ring. Okay, so I guess orange and purple are fine, except I think maybe we did purple here. And all right, so I want this portion of my molecule to come from the ketone. I want this to come from the aldehyde. Notice, again, get good at pattern recognition. This is a beta hydroxy carbonyl compound. At the same time, if I want to go ahead, I can draw the corresponding alpha beta unsaturated carbonyl compound where we've done the elimination reaction. But here's still where the atoms have come from. What do you think about that? Is that, you see, I mean, that seems like a reasonable aldol product, but think about potential competing products. What do you think you might observe as well? Because remember your problem here, which is that using hydroxide, there's only a very small amount of enolate that gets formed. So what that means is that we'll form a small amount of the purple enolate, and it will coexist in solution with both the aldehyde and the ketone. So is there another product I would expect to observe? The TAC itself, right? The self-aldol of the ketone. So that would be this product, or alternatively the corresponding alpha beta unsaturated carbonyl compound. That we would get from two of the ketones with each other. Take a look at the protons of the ketone versus the alpha proton on the aldehyde. Is it reasonable to make some of the aldehyde enolate too? Sure. pKa's of the ketone versus the aldehyde are 20 to around 17. So you might even argue that you could make that there would be actually more of the aldehyde enolate than of the ketone enolate. In any case, the aldehyde enolate looks like this. All right. So what could that enolate react with? Itself and the ketone as well. So you've got sort of a huge mess here. Here is the self-aldol product for the aldehyde. Or alternatively, that's the beta hydroxycarbonyl compound. Alternatively, you could make this alpha beta unsaturated carbonyl compound. That's what you would get from condensation of the, or the aldol reaction of the aldehyde with itself. And then finally, I'm getting tired of drawing products. Finally, you have the possibility that the aldehyde enolate reacts with the ketone. And then you have the other possibility of the alpha beta unsaturated molecule forming. Okay, so we're going to just make life a little bit easier for ourselves and say that each of these represents one aldol product, because I would accept either one as the correct answer. So we have basically four different possibilities for connectivity. You have the desired one, which is the crossed aldol product between the ketone as the enolate and the aldehyde as the electrophile. But then you have the two self-aldol products, wherein the aldehyde enolate reacts with aldehyde, or the ketone enolate reacts with ketone. And then you have the other crossed aldol enolate, crossed aldol that you get from the aldehyde enolate reacting with the ketone. So that's a mess. And frankly, if you look at those products and you think, are they different enough in terms of their properties that I would have a fighting chance of separating them? The answer is no. They all have similar polarity, and so this would be terrible. So, and And that's frustrating because in organic chemistry, we like to build molecules with complexity, and limiting ourselves to self-aldol products is kind of lame. So we need some workarounds to help us, to help prevent, to let us do cross-aldol reactions, but without all the mess. Some of the workarounds are better than others. I will give you the first workaround, which is sort of cheating, and that is to use one partner that lacks alpha protons. So you simply cannot make the enolate. All right, so an example of this, avoiding the cross-aldol reaction, would be to use, and this isn't going to give us the same product, but if we wanted to get exclusively an aldol product, you can use benzaldehyde or some other aldehyde where there are no alpha protons. Do you see that? This carbon already has 4 bonds. There are no alpha protons on that carbon. Okay, if you are thinking there's an alpha proton on that carbon, you need to go back and review skeletal structures. There, you can't form more than 5 bonds to carbon, so there's no alpha proton there, which means this one cannot be an enolate, cannot form an enolate, and therefore must be the electrophile. So if you did the aldol reaction, you would presumably make the enolate that comes from the ketone, because that's the only enolate that's available, and then you would have that enolate attack the carbonyl carbon of your aldehyde to give you that tetrahedral intermediate, and this is the new bond that you made. That negatively charged oxygen is going to get protonated by water, so I'm going to just show that directly, and it would also be acceptable to draw the alpha-beta unsaturated carbonyl compound, and if you wanted to, you could draw the stereoisomer as well. I'm not going to make a big deal out of that. Okay, so that's one way to guarantee that we never see any of the orange molecule act as nucleophile, but I would still be worried about formation of the self-aldol product with the ketone, because there's not really anything in this strategy to prevent the ketone enolate from reacting with itself, right? You would get the doubly purple product from reaction of the enolate here with the carbonyl starting material. Okay, so that lowers the number of possibilities you have. And as long as your product had a fighting chance of being more stable, your cross-aldol product had a chance of being more stable than your self-aldol product, you could probably get this to work. In this case, this is probably more stable due to conjugation between the benzene ring and the alkene and the enone. So you probably could expect this product to dominate over this one. But it's still kind of iffy. So that's a solution. It's perhaps not the best one, but it's a strategy you can use. The second is sort of also cheating by using a carbonyl compound with very acidic alpha protons to preferentially make an enolate. So what does this look like? Well, you would start with, say, an alpha beta unsaturated, I'm sorry, you would start with a beta diketone or a beta dicarbonyl compound. And then put that in the presence of some other ketone and hydroxide. The pKa of the proton that's alpha to both carbonyls is 9, whereas the pKa that's alpha to just one is around 20. So there's zero chance of making the enolate from the simple ketone. Instead, you're going to get 100% of the negatively charged 100% of the conjugate base of our beta diketone starting material, and then that has to be the nucleophile because that's the only enolate that forms, right? And we get that by having OH minus remove the proton 100% yield quantitatively from that alpha carbon. So then, when it's the only electrophile you've got left is this ketone, and then let's try to draw what the product is. Here's the new bond that we made. There would be an OH here and then two other carbons. This portion comes from the electrophile. This portion comes from the nucleophile. I suppose if you want, we can draw the alpha beta unsaturated carbonyl compound as well, which is also an acceptable aldol product. Okay, so there's no risk here of self-aldol of the orange molecule with itself because you never form any of the orange enolate. Go ahead. Will aldol products always undergo elimination, or will they stay in their alcohol form? That will depend on which one is more stable. It's a case-by-case basis thing, which is why I'll always accept either one as the answer. Yep. What else? Notice that the purple molecule does not react with itself in a self-aldol because it's 100% enolate as soon as it sees base. The deprotonation is fast enough that carbonyl compound never, once an enolate, it never sees any of this protonated starting material anymore. It only sees the ketone that we've highlighted in orange. All right? So that's your second workaround. But again, it's limited because you got to use a beta diketone as your enolate, as the molecule you make your enolate from. And what if you don't want that? So the final possibility is perhaps the best one, and your text calls this a directed aldol. And the idea here is that you use LDA to make an enolate quantitatively, and then, and only then, do you introduce the electrophile. And you have to keep it cold to avoid what I'm going to call enolate exchange. So let me give you an example of this. So suppose, let's go back up to this pair that we wanted to react originally in this crossed aldol. So I'm going to copy these molecules. And we want the purple ketone to be our nucleophile. So in step 1, we're going to use LDA, and we're going to use this in an aprotic solvent because we don't want to protonate the enolate once we've formed it. THF is tetrahydrofuran. That's an aprotic solvent that's polar. It's a good solvent for these kinds of things. You would also have this really cold to prepare for the next step, but we'll just eliminate that data point here. That's going to make, because of the difference in pKa's between the alpha proton and the conjugate acid of LDA, this is going to make 100% of our purple enolate. And then this is the conjugate acid of LDA, and remember its pKa is around 40. So it's really 100% of this enolate. And again, that deprotonation happens so fast that the purple enolate never sees unreacted purple starting material. So the self-aldol is not a problem. Then, and only then, do we add the aldehyde. And we need to do so to the same reaction mixture, but it needs to be cold, because there's the possibility of the enolate here removing this alpha proton, right? Enolates can be both nucleophiles and bases, and if you're not careful, this enolate can remove this alpha proton instead of attacking the carbonyl, and then you got the crossed aldol mess that we had before. So if you keep it cold enough, you can prevent that enolate exchange, wherein you deprotonate the orange aldehyde to get the orange enolate, and you have the mess. So instead, if you keep it cold and react carefully, you can get the desired aldol product where you've controlled who the nucleophile is and who the electrophile is. And of course, it would be fine to show the corresponding alpha beta unsaturated carbonyl compound as the aldol product too. Either of those would be fine. Okay? So, and this is perhaps the most versatile of the solutions, though you have to be careful and you got to know what you're doing. And it requires you to be working in anhydrous conditions, which can be difficult to do in the lab. So that's why there are these other easier alternatives. Okay, anything you want to ask about that? Okay, yes? Why does keeping it cold avoid the enolate exchange? I don't know. You would think that proton transfer would be easier than attacking a carbon. But experimentally, I think they observed that keeping it cold works, or at least prevents very much of the enolate exchange from happening. Yeah, I got nothing. What else? Yeah?
How do you neutralize the LDA so it doesn't react with the phenol?
How do you neutralize the LDA? Well, so it doesn't react with this aldehyde. Well, you only use a precise amount of LDA, perhaps one equivalent, and you do that carefully and first, so that by the time you get here, this molecule never sees LDA, and it never sees unreacted starting material. It only ever sees enolate. Okay, others? Okay, we've done, let's see, we've done the intramolecular aldol reaction. We've talked about the crossed aldol reaction. Before moving on, I want to point out that we've said before that the aldol reaction is an equilibrium, which means that it can go backwards. So I want to show you the so-called Retroaldol reaction, and this is the backwards version of the aldol. It's going to involve the exact same intermediates, but you're going to push the arrows a little bit different. Okay, so starting with the beta hydroxycarbonyl compound, what would the retroaldol look like? Well, first you'd need a base to remove the proton from the alcohol to give you the negatively charged alcohol. This should look like the tetrahedral intermediate that forms after an enolate attacks a carbonyl compound, because it is. And at this stage, the negatively charged oxygen can kick down and kick off the enolate as a leaving group. You might say a negatively charged carbon is a terrible leaving group, but an enolate is not a terrible leaving group relative to a negatively charged oxygen. So we can kick off that enolate and we could draw its resonance structure, but then finally we would pick up a proton from some source, perhaps the conjugate acid of our base, and that would get us to the ketone starting materials, right? So that's the retroaldol. Yes?
If that were to start from the alkene instead of
If that were to start from the alkene, good. That's just a little bit trickier, but not too bad. If you were starting from here, what would you do? Well, we've seen alpha-beta unsaturated carbonyl compounds before. We're comfortable with hydroxide attacking ketones. We've seen Grignard reagents attack ketones. We've seen cuprates attack at the beta carbon. And in order to get to the beta hydroxycarbonyl compound from the alpha-beta unsaturated one, it turns out we're going to have OH attack the beta carbon. How do I know that OH is going to attack the beta carbon versus the carbonyl? Well, it does attack the carbonyl, but that's sort of a dead-end intermediate. That would lead us to the ketone hydrate, and which would take us nowhere. So we would attack at the beta carbon. This would break the pi bond between alpha and beta carbons, and we're going to put the negative charge on the alpha carbon. From an orbital picture standpoint, it's more complicated than this, but you can think of the fact that this is a conjugated system, so some of the LUMO is on the beta carbon, and when you fill that empty orbital, you can break a bond, which here happens to be the pi bond. In any case, that puts the OH group here and gives us this enolate, and this is why water can attack, because the negative charge that goes on the alpha carbon is stabilized by resonance. And then to get to the alpha-beta unsaturated carbonyl compound, we simply need to pick up a proton from somewhere. This kind of thing where a nucleophile attacks the beta carbon or the fourth carbon is called 1,4 addition or conjugate addition. And we've seen it before once with cuprates, and this is another example. So I feel like it's easy to get lost in all these details because we're dealing with equilibria and there are many possibilities. And I think some of you are thinking, how do I know what on earth happens? That's why I've said for an aldol reaction, when you're predicting the products, you can show me either the beta hydroxycarbonyl compound or the alpha beta unsaturated one. Either is okay. How do I know which arrows to draw? Well, in a mechanism question, it's not going to be open-ended. You're going to have a starting point and an ending point, so you'll know where you have to get to. You'll just need to draw arrows accordingly. For example, if I gave you this starting material and I said push it all the way back via the Retroaldol reaction to give these two products, how would you know that the OH needs to attack the beta carbon? Well, that's the only way to do the Retroaldol reaction. So you're not going to have to guess that that happens or be able to predict that it happens. But if you understand the mechanism, you're going to know that you need to go from the alpha-beta unsaturated to the beta hydroxy, and having the OH attack at the beta carbon is the only way to do that. All right? I'm not sure if I explained that very well, so what questions do you want to ask? Yeah?
So it's not that the aldol reaction is in equilibrium with this retroaldol reaction, right? It's just reversible.
The question is whether or not the retroaldol is in equilibrium with the aldol, or is it just reversible? Those are the same thing. Yeah. So what I'm showing you we said at the very beginning that, well, right here. We said up here that the aldol reaction is in equilibrium, and we've pushed arrows forward before. I'm just showing you how to go backwards. Others? Yeah.
Going from that, I guess the second product that you made below, would the base always be a hydroxy group then?
Would the base always be the hydroxy group? If you're doing the aldol reaction, yeah. But you can there are lots of nucleophiles you could use to react with alpha-beta unsaturated carbonyl compounds. So the reason we're using that here is because the question would have said start here and get here, and that's the only way to do it. But if you were going to do a synthesis and you wanted to install another nucleophile there, you certainly could. You could go on in the next step and use a cuprate and make a new bond there. Okay. So why worry about the retroaldol reaction? It turns out it's really important in metabolism. So I'm going to draw for you now fructose 1,6-bisphosphate. You may have heard about this in an MM Bio or PD Bio or Cell Bio class. This is one of the intermediates in glycolysis. Fructose 1,6-bisphosphate looks like this. There are phosphate groups on carbon 1 and 6, and there are OH groups on carbons 3 and 4. Now, there's a lot of details there. Now focus on the functional groups. We have a carbonyl carbon, we have two different alpha carbons, and then we have a beta carbon. And look at what we have on that beta carbon. We have a hydroxy group. So fructose 1,6-bisphosphate is a beta hydroxy ketone. Or in other words, we could have gotten this from an aldol reaction. Let me highlight the beta hydroxy group. And then here's the ketone, a beta hydroxy ketone. Now, if you remember in the aldol reaction, the new bond we make going forward is the one between the alpha and the beta carbons, right? So once we've identified the alpha and the beta carbons, and the beta carbon has an OH group, we know that this is the bond we could have made via the aldol reaction. And that would make all of this portion the electrophile in the aldol reaction. That's part one of the molecule, and that would have made this the nucleophile in the aldol reaction. The purple portion would have been the enolate. Why are we thinking of it forwards? Why are we thinking of it in terms of an aldol product? Because what nature's going to do is use these exact same steps to break this molecule apart into 2 3-carbon pieces. You have a 6-carbon sugar, you want to metabolize it. It's inefficient to break it into 2 and 4, because then you got to have a whole other machinery to deal with the 2-carbon product and the 4-carbon product. Nature's efficient, it's going to split this into 2 3-carbon products, and it turns out we'll be able to convert one of them into the other, and then we can shunt everything down the same pathway. But we're set up perfectly to break this molecule into 2 3-carbon pieces because of this beta hydroxycarbonyl compound. Okay, so what is the retroaldol going to look like? Okay, we're going to have some base, and this is likely the enzyme, and this is going to remove a proton from the OH group. All right. Now, we typically, if we were doing this with, say, a simpler beta-hydroxycarbonyl compound, which I've tried to draw in a way that's similar to how we've drawn it over here. The way we would do this mechanism on our own in solution would be first we would have a base, remove the proton, and then we would draw an intermediate with a negative charge on it. And that looks like the tetrahedral intermediate that you get after you have an enolate attack a ketone. And then in another step, we would have electrons on the oxygen kick down and have the enolate leave. This reaction is enzyme catalyzed. The enzyme that catalyzes the reaction is called Aldolase. The folks that named the enzyme knew it did the Aldol reaction, so they put the name of the reaction in there. It's actually named for the reverse reaction that we're doing. That happens all over with enzymes, and it's kind of irritating. I suppose they could call it Retroaldolase, but I don't know. That didn't catch, I suppose. Because this is enzyme catalyzed, one of the things that enzymes do in catalysis, as you saw before when we did the hydrolysis of lipids with the lipase and the catalytic triad, is one of the things enzymes do is they catalyze proton transfers. And those proton transfers can either happen before or during a slow carbon-carbon bond forming or breaking step. If it happens before, it's called specific acid catalysis. If it happens during, it's called general acid catalysis. You'll learn more about that in biochem. There's some experiments you can do to determine which one is which, but for our purposes, and in some cases it may not be known. So to save time and also be general enough to account for whatever the experimental data say, we are often going to show the proton transfer step and the carbon-carbon bond breaking step at the same time. Okay? So the base removes the proton. Electrons, instead of drawing the tetrahedral intermediate, we're going to have those electrons kick down directly and break the carbon-carbon bond to make the enolate. All right, so doing that would give us the following aldehyde. By the way, this is called glyceraldehyde 3-phosphate. Some of you may have heard of that before in a cell bio or MM bio class. And then on the other side, what will we have? Well, we've got the OH group with a negative charge on it. That's with a negative charge on the alpha carbon. This is the purple portion that was the enolate. And then that enolate will be protonated by some acidic group, perhaps in the enzyme active site, perhaps from water. And that will give us the other neutral product, which is called dihydroxyacetone phosphate. And take a look at both of those molecules. They each have 3 carbons. And notice how they're related to each other. In the aldehyde, the ketone, the double bond is on carbon 1, the OH is on carbon 2. In the dihydroxyacetone phosphate, the OH is on carbon 1, the ketone is on carbon 2. And it turns out we can actually interconvert them through a couple of rounds of tautomerization. But we will stop there. Take a look at that, make sure you understand what's going on, and I will see you Monday.